Dobar dan. Dobrodošli u Srce. Dame i gospodo, dragi prijatelji, neobično mi je drago da vas evo mogu ponovo pozdraviti u Srcu na drugom od događanja vezanih uz naše radno obilježavanje 40. godišnjice Srca. Neobično mi je drago da se okuplja tako veliki broj ljudi, drago mi je da su teme interesantne, a jasno da mi je danas posebno drago da mogu ponovo u Srcu pozdraviti našega kolegu, profesora Mladena Vouka, koji je čitav niz godina radio u Srcu. Ja sam čak išao kopati po nekim tablicama pa sam ustanovio da je to bilo od 78. do 85. U to doba Mladen je bio voditelj odjela za programske jezike, vjerojatno bi ga danas svrstali u nekakvu middleware ekipu ili tako nešto. Ali u svakom slučaju, dakle, ono što je nedvojbeno, dakle, da je tijekom svojeg djelovanja u Srcu Mladen sigurno ostavio iza sebe značajne rezultate. Jedna je od onih prepoznatljivih osoba koja je činila Srce u 70. i 80. godinama. Neću previše govoriti o akademskoj karijeri profesora Vouka. Danas profesor Vouk radi na North Carolina State University. Tamo je profesor, predstojnik odjela za računarstvo, recimo idemo to tako probati prevesti na naše hrvatske uvjete danas, a isto tako i obavlja funkciju prorektora za informacijske tehnologije. Ne mogu ne spomenuti, a to je jedan od razloga zašto je isto također, mislim, posebno interesantno za nas na Sveučilištu u Zagrebu njegov boravak ovdje. On je jedan od suosnivača Virtual Computing Laba, dakle jedne paradigme koja je danas jako vezana i konkretnog proizvoda koja je danas vezana uz ono o čemu danas jako puno pričamo, o cloud computingu, ali evo imamo to sreću i zadovoljstvo da je danas Mladen s nama ovdje i da nam može zapravo iz prve ruke reći kako ta paradigma u praksi zapravo već uspješno živi na jednom američkom sveučilištu. Evo ne bi previše duljio i prepuštam riječ profesoru Mladenu Vouku.
Zorane, hvala na uvodu. Poštovane dame i gospođo, posebno mi je čast i zadovoljstvo da sam pozvan održati ovo predavanje povodom proslave 40. godišnjice osnivanja Srca. Za ovu priliku posebno bih se htio zahvaliti pokrovitelju proslave, predsjedniku Republike Hrvatske, profesoru doktoru Ivi Josipoviću, te ravnatelju Srca, gospodinu Zoranu Bekiću. I također bih htio iskoristiti ovu priliku i pozdraviti sve ovdje prisutne uzvanike, kolege, prijatelje i suradnike, kao i sve one koji slušaju preko interneta, a tu uključuju, ja se nadam, moju obitelj u Americi. Srce i djelatnici Srca su od samog početka bili svijetli primjer napretka u informatici i računarstvu tu na ovim prostorima, a isto tako i u svijetu. I zato mi je naročito drago da mi je pružena ova mogućnost da zajednički pogledamo u budućnost informatike i računarstva. Ja se iskreno nadam budućnosti Srca kao vodeće snage u napretku hrvatske informatičke tehnologije. Ja ću predavanje držati na engleskom, međutim ako mi postavite pitanje na hrvatskom, odgovarat ću na hrvatskom i na engleskom. Moj hrvatski je po prilici 25 do 30 godina stari, prema tome nisam siguran da znam svu terminologiju, međutim pokušat ću. Još jedanput puno hvala. Ladies and gentlemen, it's a particular pleasure and privilege to be here, to have been invited to give this talk at the 40th anniversary of University Computing Center in Zagreb. I started my career in information technology here, and I have always had very warm feelings for everybody in this organization, and I think they have achieved and made tremendous impact in this region and in the world in what they've done. So let me start out by telling you what I'm going to do today. I'm going to look at the new paradigm that's called cloud computing that has a promise of solving a lot of problems we have been solving for years now. We are being flooded by data. It comes from all sorts of directions, And there's what you could call exabytes of data coming through the networks, being deposited in various storage devices. There is a variety of information being collected by all sorts of devices that do not necessarily produce structured information. In fact, 80% of the data is expected to really be unstructured in many ways. And mistakes that people make when they look at that data or do not have the proper analysis behind the data can be quite costly. In fact, maybe 40% of the managers say that they use wrong information at least once a week. This is not trivial. There's a huge amount of data on the internet, and the real challenge there is collection, collation, and finding of the information, because the data is useless unless it's analyzed properly and turned into some useful information that can then turn into decisions. So I've said the word exa and zeta, but I'm not going to use that very much because those are just very large numbers, and for most of us it doesn't make very much sense to think about it. It's just a huge amount of information. The question is, what can we do with that information? It's being generated by supercomputers. Supercomputers in the exaflop range will be coming out in 2018, and I'm pretty sure you've seen this diagram. This is from the top 500, and if you do an extrapolation, we're about here in 2018 or so, and we are likely to have computers that work at exaflop rates. What they generate, of course, is going to be a huge amount of information, and most of the problems are actually getting that information out of the supercomputers. But if we just go an order of, 3 orders of magnitude lower, we find that the fastest computers today are about 2.5 petaflops, mostly in-memory calculations, and the fastest, embarrassingly, parallel computations. There's a loosely coupled network called Folding at Home, which probably does anywhere between 6 and 12 petaflops. Google processes about 25 or so petabytes a day, and the CERN Large Hadron Collider promises to generate 15 petabytes per year. So obviously that information is a problem. Well, it gets worse. Global internet traffic runs about 21 exabytes per month, at least it did last year. Mobile traffic will reach over 2 exabytes per year by 2013. If you look at just the statistics of how many computers have been sold and devices, there's at least 2 billion devices in the world, and if you could actually use all of those at the same time, you would be getting exaflops of processing power. And in general, the flood of data is just getting bigger. So the question is, what is the problem there? Well, the limitations are many. Storage, for instance, is a limitation, but not really. It's just a question of money. If you have enough money, you can get enough storage. It's exa capable, and you can buy essentially enough storage to store exabytes of data. People do. Networks are a little bit on the slower side. You have to move the data. You can do 100 gigabytes today, but there's enough channels, and you can actually move enough data so that you're really moving exabytes of data if you think in the networks in the world. But it's getting to be a bit more of a limitation. Computers, whether they're tightly coupled, like supercomputers, or loosely coupled, like the loosely coupled network that I mentioned, they are still capable of peta and probably exaflops in 2018. The problem is input and output, getting the data out of the fast computers onto storage or onto somewhere else. The latency, if things are not tight, if you need calculations where many of the processors have to work together, it's hard to get them to talk to each other, and there's a special premium on fast interconnects. Power is very expensive, cooling is very expensive. So there is a limitation there. But as you go down this list, it gets worse. Trust is really the real problem. Do you really trust someone to hold your data? Do you really trust the analytics somebody gives you over the internet to actually look at the results and just take them at the face value? The confidentiality, the security, the privacy, the science behind it. But the biggest limitation is us. Everything above us can take a lot of bits per second. We can only take about 20 bits per second, believe it or not. As an illustration, and I'm not going to go into this, I'm going to show you 10 slides or so. I'd like you to do the following. Watch the slides and tell me, make a note, how many dots do you see? Okay? So let's say this side, look at the first 3 slides. This side, look at the next 3 slides. And this side, look at the slides after that. How many dots in the blue square? 12. But that is not because you counted them, because you knew that. So that's a pre-coded information, right? How many dots were in this slide here, for instance? Right? So you can probably track things down this and this, maybe if you look around. But once it gets past about 5 or 7, it becomes a problem, unless you structure it, unless you bring it together into blocks that you can recognize. Probably most of you could count this, right? Because it's nicely blocked. In fact, if you code things right, you can count all of them. You just read the number over there, right? There's no problem. So it's important to get the data reduced to something we can deal with, and deal with in the time that we have to make decisions. And people are getting there. For instance, anybody watch Jeopardy? Yeah, I'm sure there are versions of that around here. There is a computer called Watson that seems to be very clever. It played against humans and won on questions like, you know, what is the coldest day in the year or something like that. And Watson is a blue gene type machine with 22 terabytes of storage, 90 servers, and something like 80 teraflops of computational power and 1 terabyte of memory. And you would think that that would be able to do a lot, and it does. It's a questions and answers tool. It has natural language processing capabilities. It's a text processing analytics tool. It does data mining. It does pattern matching. But it was trained to sort of play the game. But what it really does very well, it reduces the data that it has into manageable small number of bytes that a human can understand. So for instance, when it talked back to people, it would sort of give you 3 possible answers: purple, something else, and gives you some probabilities. I don't think anybody wants to absorb the probabilities, but if you're, for instance, a doctor, and the machine tells you that the illness might be this, this, and that, it may trigger something in your mind. You may say, aha, okay, maybe I should look at that. So there is this ability to collect the data, look at the data, and then, although not reason about the data in a human fashion, suddenly provide précis of what is coming out in a way that a human can handle that. So that's one way of reducing the amount of data. And certainly when you're talking about exabytes, there's no way a normal human being would be able to do it without help. Analytics is going to be probably the most important part for over the next 20 years. What you do with the data, how you deal with the data, at what granularity you deal with the data, and whether somebody can trust the data that you produce and the results that you produce is going to be really what will make or break all these large amounts of data for any kind of useful presentation. So you might have a range of things like in situ analysis. If you have a supercomputer where you cannot push the data fast enough out, you might have post-analytics for the types of things that I just showed, like Watson. You would want to have trusted hierarchical analytics so that you can actually trust the data that come to you. Companies that do searching used to be trusted. Nowadays, you're not sure whether the first thing on your list is because somebody is paying them or because you actually are looking at something that is most relevant to what you want. In fact, very often you will find that your data are so large that you cannot really pull them in and look at them. You will have to take your algorithms and move them to the data. So the question is, what can help you do that? If the data is sitting somewhere in Switzerland, in Srce, and you cannot pull them back here to study them, then you have to write your programs and move them over there to do the analytics. Can you do that? Can you trust the environment in which you're going to run? If you have movable data, that's another situation. Do you really want to let the data out of the space where they are to somewhere else? I don't know. It depends. So the environment that I think can help in this is something that we call cloud computing. But cloud computing means many things to many people. And when you talk to them, you'll see that some will say that cloud computing is this, some think that cloud computing is virtualization. But we all have what I would call big data. We have all data that's important to us. Big data could be 1 gigabyte for one type of problem. It could be terabytes and petabytes of data for someone else. How you analyze that and how you deal with that may have to be done in different environments. You may have to have a desktop. You may have to have high-performance computing facilities. But it's quite certain that scientific discovery, education, and management of critical information technology systems will not happen unless this is under control. And so the question is how to go about it. People will expect different service levels. Most of us live up here. I really don't want to know except what I need to know. I want to get my service, get my information, and get out. And I want to know as much as I need to do my work. More people might be interested in doing services that are really services underneath all these services, search engines. And they might be interested in service integration. They might be actually interested in service development. They might be interested in actually writing the cloud computing software. But most users live at the level where they really want what they need for themselves. How to give them that? Well, the answer is you've got to have it. You have to have an environment which it has at least the number of components that I'm going to go through. You have to have some hardware on which you're going to run. Whether the hardware is bare metal, which means a computer into which you're going to load an operating system or something like that, or whether it's a virtualized environment where you're going to have virtual guest operating systems running around, either will work, but you have to have it. You have to have some kind of a client portal that you can get to that set of machines and that environment. You will always have to have a help desk and training and education about whatever you do, including the environment. And you will always have to have authorization, authentication, and accounting because you have to get into the system. With new systems, you will have to have some kind of interface to the network and large amounts of data. The bare metal, virtualized environments and resources will come in various flavors, and the functions will come in various flavors. One thing that a lot of people today still neglect to build into systems like this is a very extensive collection of provenance and metadata. Provenance tells you how the processes have changed, how the data have been transformed, who has had access. Provenance and metadata, data about data, are the key to security, the key to proper analytics, the key to understanding how the system works and whether you are running out of resources or not. You need privacy and security guarantees. And one thing that's really odd right now and is not working too well are licenses. The vendors have really not gotten used to this world in which I can use a license 24/7, for instance. If you have a machine over here and it's in your lab, normally you would expect maybe 5 to 10 students to be scheduled per seat. And so they might be there between 8 o'clock in the morning and 8 o'clock in the evening. If you have a license for exactly the same software that is being accessed from outside, you are using that license 24/7. So you are certainly, as a person who is buying licenses, gaining from that. But vendors are not very happy with that. And those licensing issues are still out there and are still being discussed. Privacy, of course, and security is essential. If you don't have that, you're not comfortable using systems like this. You absolutely have to have reliability and fault tolerance. The numbers that are being talked about as anywhere between 3 nines and 5 nines is what you really need, which means maybe few or no failures in a year. Maybe 3 minutes downtown in a year gives you an availability of about 5 nines. And you can do that in distributed systems, in clouds. But there's also other things that go into this bucket of reliability and fault tolerance. You can, if you do it right, you are not dependent anymore on individuals who'd be single points of failure in your system, because there's always an option, there's always a failover. You want to have, of course, a number of domain services, analytics options, and other attributes that you can deal with. And some of those are things like hardware as a service, infrastructure as a service, platform as a service, and so on. The most important ones, turns out, are actually location as a service. You want to know where your data is, in most cases. Maybe you don't care, but if it's personal data, if it's your health records, you sort of probably wouldn't be very comfortable if it's floating all over the world. It would be better if it stayed in this particular country. And one thing that gives you a lot of fault tolerance is the ability to import and export software, algorithms, and the currency of clouds, which tend to be images. So that if you're unhappy with the services somebody is giving you, you can pick up your toys and leave. It's not very easy to do. Vendors are not very happy with it. Vendors would like to lock you in to a particular environment because then they have a captive audience. But the beauty of cloud computing is that you can actually, if it's done right, decide that you're going to change vendors, you're going to change anything in it that you want, and you will still be getting the services that you need. When you look under the hood of a cloud, you see some interesting things. You see that you have some kind of a workflow control plane, a control plane from which you can really tell what you want done. That works mostly unbeknownst to you in the heavy lifting area below, where the magic happens, the computing happens, the data storage happens in a synchronous or asynchronous mode. And the algorithms and requirements for analytics are done really at the concept level. And then the software below that creates appropriate instructions and scripts and whatevers to make things happen. And then the end users are mostly interested in the knowledge, analysis, analytics, decisions that they can make from that. That requires a world in which the devices that are underneath are actually analytics aware. And there aren't many like that around. And under normal circumstances, if you're dealing with gigabytes of data, that's less important. It's much more important when you're dealing with exabytes of data, where you cannot really move devices around, you cannot move data around too much, and the data as they come in need to be processed on the fly. So that's a challenge, and it's not a solved one. So let me give you a few examples so you will understand what I'm talking about. NC State College of Management researchers work with various companies, pharmaceutical companies, for example. And these companies have certain amount of apprehension when it comes to dealing with open search engines. Because when you go to, for instance, an open search engine, everything that you do is recorded. And if you're looking for something that's patentable or something that you would like to keep proprietary or something that may be intellectual property eventually, the way you do the searches can actually reveal what you're looking for. So some of those companies are uneasy about going to public places and doing it, and they prefer to construct their own search engines that would actually do the searching of the internet in a much more privacy-preserving and security-preserving way. And so they have constructed an environment to do that, and they have used enabling technology such as IBM's JSTART, which is not quite what Watson uses, but is the same type of idea: natural language processing, content analytics packages, something that's called Big Sheets, which is a large sort of spreadsheet that can handle all sorts of data. And they have asked us to put it on to the specialized subcloud that runs on something that's called the Virtual Computing Lab at NC State, which I will talk about a little later, which is essentially a cloud computing platform. And their environment was not that sophisticated. It was something like 12 IBM Blade Center HS22 blades, which have something like 1 teraflops or so of processing power, several terabytes of storage, and about half a terabyte of memory. And they had front engines which would go and search the network for what they needed, pull that back in, and then they would do the analytics, looking, for instance, for drug discovery type elements, papers, what everybody is doing, so they can get ideas and collect information and then produce things that they're interested in. So we constructed something that's called, which is in beta testing, analytics subcloud, that essentially has a crawler that goes around databases, webs, clouds, pulls the data back in, and puts it into the VCL data banks, and then it's being processed and analyzed by the end users for what they need. And it would crawl for weeks, and it would bring in terabytes of data, and they finally reduce that to maybe a few hundred gigabytes of useful information. So there's a considerable amount of data reduction happening in the process. And that's in the space of text analytics. The same facility, Virtual Computing Lab, allows you to also dip into the space of high-performance computing if that's what your analytics requires. For instance, you can steer this particular set of centipedes to go and get what you need, but you can also, if it's necessary, you can run simulations either locally on the high-performance computing component of the Virtual Computing Lab or somewhere else. And this particular example was run sometime in the October-December 2010 timeframe on a fairly regular basis, because at that time we had a spill, the oil spill, if you remember, in the Gulf, and it was of considerable concern. And this particular model was one of the models that was used to track and analyze the issues that arise from that. And that works on the high-performance side of the whole cloud. So you can go from basically analytics which worries about post-processing and asynchronous to analytics which worries about day-to-day runs. And in order to help us that, if you remember when I started out here, one of the things is that you do have to have the proper education and training. And we actually have an institute at NC State which is called Institute for Advanced Analytics, that has a mission of training master students in the specialty of analytics, mostly focusing on business analytics at this point in time, but thinking of doing it perhaps in the security space and in a few other areas. The enabling technology there, in addition to the cloud that we have, are, for instance, SaaS analytics products that do an excellent job. And so the curriculum is based on using and training people to use those products for the future work. In fact, it turns out that when you look at the Exascale clouds, I think that what will happen is that there will be a need for very frequent exchange of information and algorithms with other clouds, because your own environment is not going to extend into all parts of the world, and you will not have priorities there, and you will not have the right tools. But if you can exchange the algorithms, if you can exchange the data, and you have some trust in that domain, then you can do a lot of things. We will obviously have to have very well-defined interfaces for data and algorithm exchange. It's, if you ever worked in that space, you know it's not easy. And engaging in automatic summarization of the real-time data is fine, except my summarization may not be useful to you at all.
I may summarize things in one way, give you a whole chain of information, and you may not be able to use it. So the question now is, how can you backtrack, and how can you perhaps provide some alternatives to that? Obviously, the whole business must be secure, trustworthy, and privacy aware, and privacy preserving, or people will not use it. So that's the sort of a shades of things to come, where we have to go in order to make use of the huge amounts of data that are coming down. So now what I would like to do is spend a few minutes telling you how we have been doing it at NC State in an environment which is a cloud computing environment called Virtual Computing Laboratory. It's an open source product. It's actually a Apache incubator, Apache incubator, and you're perfectly welcome to go to this URL, for instance, and look at the Apache component and download it and look at it. It requires other products than just VCL, but they're all open products. We currently have 2,000, it's a private cloud, which means that it's not open to the public. It's open only to the students at NC State and faculty and students in the state of North Carolina. And we have something like 2,000 plus blades, maybe something like 7,000 cores. We only have 2 people supporting all of that. 2 FTEs. I have to really be careful when I say that. It's not 2 people, it's 2 FTEs, full-time equivalents, which means that there is a range of skills. If you remember the triangle, the inverted triangle, there are skills that have to do all the way down with development and construction of complicated things, and then lighter stuff. And for that, you probably need 6 people that have bits and pieces of that knowledge, but they do other things. So larger organizations can afford that. Smaller organizations may not be able to. About 700 of our blades are sort of sitting in a general mode. They will serve to you things like tabletop, desktops. They will serve to you clusters of machines or servers. And then the rest sit in the high-performance computing mode, because we have a lot of researchers, and our researchers are very interested in being able to use those facilities. And the interesting thing is that we have the same infrastructure of 2,000 machines, and we can move them from one function to another basically at will in a matter of minutes. And that helps us balance the resources in where they are needed and when they're needed. The system at NC State is open to about 40,000 plus students and faculty, but all of North Carolina, which is using Shibboleth as authentication mechanism, as authorization authentication space, identity management, there's 250,000 students who have access. And we deliver something like 250,000 service reservations per year, and maybe 10.5 million of CPU hours per year. For us, it's very cost effective. For us, the cost is between 3 and 30 cents per CPU hour. But you have to use those hours, because if you don't, the cost goes up. So we are very proud to say that we were cloud when cloud was not really cool yet. The VCL production life started in the fall of 2004. And it was driven basically by our inability to serve our students with what they needed. And so we constructed the environment and this is where we started. Cloud didn't really, on the vertical axis is the search volume for the term cloud computing, grid computing, high performance computing, supercomputing. And on the horizontal axis are just the dates. And the cloud computing really didn't exist, at least not in the minds of most people, until about October 2007, when IBM and Google announced jointly a cloud. And after that, it just took off. And it has been climbing. It's certainly surpassed the interest in grid. It has always really been above the HPC and supercomputing. And the question is, can one live up to these expectations? Expectations are very high. And the answer is, I think we can, but one has to approach this and knowing exactly what is going on. If the cloud is not offering you all the functions that I have mentioned before, you have a problem. This is the entry point into our cloud. It's a web page to which you can log in. You can on-demand reserve the resources. I'm not going to go through the details of that, but if you are interested, it's a self-service, it's open, it's modular, it's very flexible, we think it's cost-effective, it's reliable, and if you're interested, we will be very happy to send you a taste account so you can go and try it out, see how it works for you. It seems to work pretty well across the ocean. We have tried it from Europe and from India and from South America, and for many things it works fine. For some it won't, because the latency and other things make a difference. The services that you get are bare metal or virtual images. Images are stacks of software. They may include a hypervisor or not. They may include operating system. Usually they do. Or they may be just the applications on top of that. And you can get single seats, as in a desktop. You can get multiple synchronized seats. So I could have reserved for all of you here maybe 50, 60 seats, and you would all have at 2 o'clock in the afternoon, you would have had them until 4 o'clock. And you could have worked on them. I can make long-term reservations for servers, and I can do subclouds. I can, on this system, host any other cloud that is of interest to us. I can put a Hadoop engine on it. I can put Eucalyptus engine on it. I can put anything else. Because it allows it can act as a provisioning engine, or it can act as the actual cloud itself. And in our case, it also provides high-performance computing facilities. It can also use agents to get into facilities that we don't own. For instance, I can hook up into other clouds and borrow the facilities from there. We at night creep into laboratories where we then use the machines which are not being used at night, add them to the collection, and then in the morning we get out of the lab. And we can go to supercomputers and other mainframes if we need to. And of course, underneath that, there's a whole storage bus that actually ranges from trivial amount of storage to terabytes and terabytes of storage. And you can have stateless services, which means that they don't remember anything after you stop using them, to persistent mode services. Most of our users use them in augmentation mode, which means that they have their laptops, their desktops, and when they need things which are not available readily on their laptops, they're too expensive, cannot fit, or anything like that, then they bring in the virtual computing lab. But you can use them also in consistent, persistent mode, and that works too. So a quick look inside. This is the top-level architecture of VCL. It has a web interface, as I already mentioned. It has a manager. It has some authentication service. It has a database, and it has distributed management nodes which know where the currency of VCL is, the resource is an image, and knows what you're allowed to get, and goes and gets that, loads it on the available resources, and then lets you use it. Now, if the available resources are not available, then of course it will tell you that, and you might come back later or never, depending on what you're asking for. We also have a lot of fences around VCL to ensure that no evil is perpetrated out of that particular space. We have network sniffers and monitoring of the facilities, and that works pretty well. You can run VCL, for instance, in a way where a user comes in, logs in, goes to a scheduler, goes to the database, gets the resource, and goes to the server. Once they have been authenticated and have gone through this line, then the scheduler basically switches the direction, or this VCL switches the direction. It's not really looking at this anymore, but you're talking directly to the server. Okay? So you don't overload the system with unnecessary traffic. This is protected traffic here, It's usually SSH, or it's some kind of encrypted traffic, encrypted channel. And usually we produce an IP lock, which means that only that particular user can get to the server. This is a very quick look at the internals, and I'm not going to spend any time on it. But it's very, very modular, and you can actually replace just about any of these modules with something else. IBM, for instance, is very interested in this solution. They're already shipping it or planning to ship as part of their educational suite or suite for educational institutions. And they have replaced many of these things with other things. The VCL scheduler and web browser, for instance, with an IBM browser, IBM web server. Database with DB2. We are using MySQL, but it could be something else. And you can write little modules which will plug in into anything you want. So without going further into that, there's a lot of that information online if you wish to. It's very, very flexible. It gives you the option of adding, locking yourself into a vendor, going with a vendor solution, and also backing out. And this is the important part. Security as a service is actually available within VCL. You can identify the security levels you want. There's a very sophisticated policy-based privilege tree that maps things out. We use timeouts and similar facilities to IP locks to essentially ensure that only authorized users can get into the system. And we have VLANs underneath that which can block out groups of machines or single machines for more secure management. And of course, our students all have VPN access to the system itself. There's traffic monitoring that I mentioned before. So we are very comfortable with that. It's not that it's 100% secure. Our faculty tend to be the biggest culprits in this business. They would give machines to students. Students get root, by the way, on all our machines, because when they're finished, we just wipe and clean. But they would install all sorts of things, and not maliciously, but leave password as a default password. And the next morning, their machines are compromised, and we bring them down. But that happens on the periphery. They get isolated, and everybody else is protected. So it's a very good learning environment. There are runtime dashboards that you can monitor the behavior of the whole system to see what it does and what it doesn't do. And we offer the outside world a lot of provenance and metadata. And we tell our users how often an image has failed or not failed, what reliability they can expect from us. All of these things make our users very, very comfortable with the environment because we're not really hiding anything from them. And you can implement VCL in various forms. You can go from partnerships with people who already have it. VCL community consists right now of a large number of universities in the US and some abroad who are either running pilots or running on VCL. And you can go and operate full-blown VCL. I think the current version is 2.2. But you need specialized people to do that. You can partner regionally or at a continent level if you want to with some of those who have. And you can do with storage what you want. You can own the data stores if you want to, or if you don't care, then things are done behind the scenes for you. The scalable part about the system, and I think also a security enhancing part, is that the resources are intelligent. They know how many licenses they're allowed to run. They know who can use them or not use them. They know where they can run or not run. They are quite cognizant of the space in which they operate. And therefore, you can easily scale that up because we as a centralized facility maintain only maybe 10 or so images out of 800 or 900. Everything else is maintained by our users, by research assistants, by professors, by technicians, and so on. And we have really not had major problems with that. There is some training required, but otherwise things work pretty well that way. So it unburdens the centralized IT from all these things. What I think is coming with the Exascale data and computing is that you may not want to run all the resources that you need for your organization. You may want to install something like a VCL or a similar cloud facility and have some basic set of resources that you can use locally, and then everything else is brokered from outside. You would go, for instance, contract with some outside cloud provider for certain resources, either in peak hours or off-peak hours, whatever works for you. And what you really have is locally is a cloud that can take over the functions if the outside world fails and maintain your critical functions, but anything else can be bought from outside. That may work for you or not. It's not very clear what the cost model is at this point in time, but I think people are looking into that, and this is a useful, a very useful model to think about. So how much does it cost? Well, that depends. How much money do you have? You can actually support 200 to 400 simultaneous users in a virtualized environment with something like $100,000. You can already get a decent environment. And if you work using the cloud in augmentation mode, you can support with that 20,000 students very easily. If they use it as their main access point and lock it up for the day and do nothing else, then of course you have a problem. But if they come in and use it for a few hours to do their homework or do something else and let go of the resources, which is what we encourage, you can with this kind of resources support 20,000 students quite easily. Operational cost can be also pretty good. You can maybe $200 per blade and 2 to 3 FTEs to run about 5,000 units and license costs. You can really run the operation. It's not that expensive. You do need a wide range of skills depending on what you're doing, whether you partner with someone or whether you're running the show on your own. I personally think that today, for a relatively modest investment, an organization, a state, a nation can provide first-class, full control, scalable, secure, and sustainable resources, information technology resources, a cloud, and anything else they need to support daily operations, education, and critical services and applications. It's possible. Whether people do it, they're sitting on the fence a lot of times. They're not quite sure which way to jump. But it's doable. You have to know what the capacity of your resources is. So for instance, this is the growth of usage of VCL since 2004. You can see where holidays come in, right? Very easily. There are peaks and valleys. And you have to know how many concurrent users you are going to have, because if you cannot support concurrent usage of, say, 700 machines, virtual or real, you have a problem, because you will have unhappy customers and your availability is going to drop below the numbers that they want. But on the other hand, you have to ask yourself, what happens in here, in these valleys here, right? Because when I have this laptop is not doing very much right now. It's sort of sitting there idly most of the time. Yet I'm grabbing a full-blown resource. So the question now is, can I have a big stack of virtual resources and together they add up to the right utilization, or do you do something else to backfill the gaps? And what we have done at NC State, and one can do it differently, we have essentially taken high-performance computing batch jobs, put them in the background because they can always be slowed down, they can always be backlogged, if you like, and we have put them into as a backfill, and that does wonderful things. And if you look at the usage of the facilities over one day, contrary to the popular belief, students don't work earlier than 8 o'clock in the morning and past 8 o'clock in the evening. And you can fill this in with useful work if you have it. There's a lot of things that can be done. You can turn the machines off if it's too expensive to run them. That gives you enormous cost savings and makes cloud computing usable. Cloud computing works only if your utilization is in the 70 to 80% range overall, not necessarily for a single machine, but overall. And in our case, for instance, economics runs something like this. If you just take desktop augmentation without backfill, then per year it might cost you, considerable sum of money. Per CPUR it might be $1 to 34 cents if you don't count the, and by the way, the largest cost in cloud computing is not hardware, it's people who you have to have around to actually run things, even when you have a relatively small number of people. But if you use the backfill, it becomes something like trivial, 12 cents to 8 cents per CPUR. That's a pretty good price. Who you make the arrangements with in a research institution like University of Zagreb, I would say that high-performance computing probably could be a very nice backfill. But you could run something else. You could run payroll calculations in the background. You could run something much more mundane. So I personally think that it's possible to make things very economical, very easily, but it does require organization. Where we are going with all of this? Well, we are currently IBM is actually providing worldwide support for VCL. In other words, it's not just the University of North Carolina, but it's also a bigger organization that provides help desk and similar type of supports. We can do all sorts of interesting things, and we are beginning to hook into clouds and other facilities. We are constantly enhancing it. It's an open source product, so it's an open community, and others are contributing as well. And we see VCL, or in the future perhaps another variant of this, as being the key to being able to deliver good education to our students, good resources to our researchers, and be very concerned and very conservative with the spending of the money that goes with that. So in summary, at exascale analytics level, I think you will need a lot of granularity, a lot of analytics aware clouds or cloudlets. There's lots of plans everywhere in the world what to do with the clouds. Analytics is big. Cloud computing on the commercial basis, where they sell you hours on the machine by the SIP, Amazon EC2, or Microsoft's Azure, or Google at different levels. Our experience is that clouds work if utilization and reliability are high, if end user access is easy, if functionality is diverse, and in fact if the user remains in control. The key there is the user needs to remain in control. If you want to let the control go, that's okay, but it's your choice. But if you just lock into another vendor, the problem there is that it's no different than what has been so far. And so whenever you construct a cloud, you have to ask yourself, does it do all those little bubbles that I showed? And if it doesn't, you should be very, very wary. If you need more information, please don't hesitate to go to vcl.ncsu.edu and browse. If you want a taste account, I'll be very happy to provide one. And I think that's it. So, and I think I also kept the time. So thank you very much.